Hi, welcome back. We are in Lecture 4, Segment 2. In this segment, we're going to do a lot more math. So we'll go through the calculation of the correlation coefficient. And it'll look like a lot of math, but it's not much if you think back to the descriptive statistics and the calculation of standard deviation and variance. There's really just one twist on that calculation, and we'll get the correlation. So the important topics to take away from this segment are the mathematical underpinnings of the Pearson product moment correlation coefficient, little r, and the concept of covariance, which I haven't really explained yet. So I'll use little r in italics to refer to the Pearson product moment correlation coefficient, the full name for what we typically just call correlation. And conceptually, what r represents is just the degree to which x and y covary relative to how much they vary by themselves or independently. So a way to think of it down at the bottom in the last line here is a ratio of covariance to variance. And that's what you'll see in the math. So I'll walk through the calculation of the coefficient r two different ways, and hopefully by doing it two different ways, the concept will sink in through the math. First, we'll do it from what I call the raw score formula. What I mean by that is we'll just take people's scores as they are, raw scores. The second way is we'll convert their scores into z-scores. Remember from Lecture 2 on descriptive statistics, we talked about how to convert any scale into a z-distribution. We can take z-scores and get the correlation coefficient that way. As I said, this is pretty easy to pick up if you think back to our calculations in Lecture 2 on descriptive statistics. So let's revisit the Linsanity example. What we did there was we calculated some statistics, some summary statistics, for the basketball player Jeremy Lin over the course of 10 games. So we calculated his average or mean points per game, and we calculated his variance and standard deviation. Remember the way we did that? To get average, we just sum points per game, divide by the number of games. So the sum was 227, 10 games. He was averaging 22.7 a game during that stretch. To get to variance, what we did was we calculated deviation scores. So here are all the deviation scores in the middle column. Then we squared them, and then we summed the squared deviation scores. That's sums of squares. Divide that by n, and that gave us variance. These were the results for Jeremy Lin. Again, his average 22.7, standard deviation of 9.6, and variance of 92. Remember the notation, the sum of squares and mean squares. The mean squares over n is the variance. So to calculate the correlation coefficient, you just need one new concept. It's the sum of cross products. So remember, to calculate sums of squares, we went through this process. We calculated a deviation score for each game, or here I said subject, but it's each game or each case in the sample. We squared them, we summed them to get sums of squares. You do the same exact thing to get the sum of cross products. Except now we're dealing with two variables, right? Because we're correlating x and y. So for each case, or for here each subject, I want to calculate their deviation score on x and their deviation score on y. That's why I now have the subscripts for m sub x here and m sub y. So the mean on x and the mean on y. For each subject, we'll then calculate their cross product. That is, I'll take their deviation scores and multiply them. Then I'll sum the cross products, and that gives me sum of cross products, analogous to sum of squares. So let's walk through that. The correlation coefficient is the sum of cross products over the square root of sums of squares for x times sums of squares for y. Again, conceptually, think of that as just the degree to which they covary relative to the degree to which they just independently vary. And this symbol right here just says square root. It's a little hard to see. So we're taking the square root of that product. Now remember, to get sums of squares x, I showed you how to do that in the Jeremy Lin example. Just calculate the deviation scores, square them, sum them up. That's sum of squares. I could write that out sort of more formally, just take out the square root and write it this way. That's sort of long-winded, right? We don't do that. But I did it here just to demonstrate the similarity to sum of cross products. So we have sum of squares x, sum of squares y, and then sum of cross products for x and y. So then if I elaborate this first formula, I can rewrite the correlation coefficient simply in terms of deviation scores, which you've already seen, you already know how to calculate from lecture 2. So it's actually a pretty easy calculation. And in fact, we're not going to go through and do one of these by hand. It's a bit tedious. We'll let R do that work. What I would like to do is show you the formula from z-scores and show you how they're equivalent, because I hope this drives home the concept of correlation. So instead of working from the raw scores, we could work from z-scores. And the formula for correlation at the top here is the sum of the product of the z-scores divided by n. So for each individual, I could get their z-score on x, their z-score on y, take the product of that, and sum them all up, and take the average. If you think about this for a moment, what do you need for a strong positive correlation? You need, if somebody's above average on one measure, they should be above average on the other measure, right? What that means is if their deviation score, how far they differ from the middle of the distribution, if their deviation score is positive on x, their deviation score will probably be positive on y. A positive times a positive contributes more to the sum. Same with z-scores, right? Remember, the middle of the distribution on z is 0. So if you're above average on x, you'll have a positive z-score. If you're above average on y, you'll have a positive z-score. And if the two variables are positively correlated, then most likely, if you're above average on one, you're above average on the other. What if you're below average? If you're below average on one, then you're most likely to be below average on the other. A negative z-score times a negative z-score gives you a positive value, again, contributing to the sum of cross products, or here, contributing to the numerator in the formula. What happens if there's no correlation? Well, that means sometimes you could be above average on x, but below average on y, and vice versa. So a lot of times you'd be multiplying a positive times a negative, and a positive times a positive, and all of those would wash out. If you summed them, you'd come up with 0. So hopefully you can see by doing these calculations how you get correlations on a scale of +1 to 0 and 0 to -1. So let's just write this all out. This is just simple algebra. So here's the formulas for z. That's from lecture 2. Here's the formulas for standard deviation. Again, just from the descriptives lecture. This is just rewriting that. What I want to show you here is the proof of equivalence between the raw score formula and the z-score formula. So if I write out the z-scores in long form, what I have is still in the numerator is x minus the mean, but in the denominator I've written out standard deviation in long form. So it's the square root, again that's square root, of variance, which is sums of squares over n. That's standard deviation. Remember, in the numerator of the z-score formula for r, we had the product of the two z-scores. And I'm going to sum those products. So I'm taking this term, the first z term, the second z term, and plugging them in to the formula for r. So we're writing out the formula for r in long form. It looks ugly, that's why I started with the short one with the two z-scores. Now what I'm doing is writing the entire formula for r. Going from this top equation to the second equation is just now going in the reverse direction and simplifying this algebraically is equivalent to the second equation, which is exactly the raw-score formula. See, look what's in the numerator, sum of cross products. What's in the denominator? Sums of squares x and sums of squares y. So by expanding the z-score formula and then using basic algebra to simplify it, we get right back to the raw-score formula, just to show that they're equivalent. We could go either way if we were doing these by hand, but again, we won't do them by hand. We'll let R do the work. So that leads me to the final concept in this segment, and that's just variance and covariance. So variance, you remember, is mean squares. It's the sums of squares divided by n. Covariance, I'll often refer to as COV. That's just like variance, except it's the sum of cross products over n. And correlation is just standardized covariance. And it's standardized so that the correlation coefficient falls between +1 and -1. A final note on the denominators in these equations. Some of you who are familiar with statistics and have done these calculations before might have noticed that I used n in the denominator in all these equations. And that's because I'm still in the realm of descriptive statistics. When we're doing just descriptive statistics on samples, we'll use n in the denominator for these formulas. As we move to inferential statistics, we'll use n-1. And when we do that, I'll explain that subtle difference. So to review this segment, the most important thing to take away from this is obviously the math, understand where this correlation coefficient comes from mathematically. And again, I think it helps to drive home the concept if you work through the math. So if you're not familiar with these formulas mathematically, force yourself to try and work through them. It does help reinforce the concept of correlation and covariance. And covariance will be an important concept as we move forward, especially into multiple regression and the analysis of variance.